lecture. Okay. For those of you taking the lab, go ahead and look for that email tomorrow and Monday about the lab. Go ahead and get the lab book and do the safety, which should be the first one in there. It's Tech 0430. The safety, laboratory safety, is what we'll be doing on Wednesday of next week. First lab is Wednesday of next week. It's on those designated times, whether you are live or you are online. There's going to be a live pre-lab lecture during that scheduled time if you are live or if you are online. So please make sure you make time for that. That's why there's a time associated with this time. We didn't associate a time with it last time, and it really messed things up. So I want to have that pre-lab lecture, the setup for the quiz, and then the instructions on how to do the following labs. This lab is just going to be a pre-lab lecture, look around the lab. Well, for the online, it'll just be telling you where things are. Then go ahead and do that quiz online. The quiz will be a Zoom proctored exam on Canvas for the live student, for the online students, and it'll be live with your instructor in lab with those live students. So go ahead and plan for that next Wednesday. Be there on time and be ready to work on that first lab. Okay, now that we got that out of the way, let's go ahead and are there any other questions right now concerning the lab or our class?
Even if our lab is on Thursday, we're still having it on Wednesday?
There should be no labs scheduled on Thursday. All of our labs should be scheduled on Wednesday.
Oh, yes. My apologies. I looked at the wrong day.
So, okay, good. I'm glad I'm not incorrect about that.
Thank you.
I think we have an online and a live lab at 12:30, and then an online and a live lab at 3 or 3:30. So they should all be in those timelines. Okay. All right. Nobody in the waiting room. We got about 38 of our 60 people here, so that's a good place to start. So what I'd like to do is I'm going to go ahead and share my screen and start picking up where we left off last time. Okay. So while I'm doing that, I'm going to go ahead and gallery mode over here so I can see whose cat is being affectionate today or not. So there we go. All right. So as always, please, ask questions or put it in the chat. I'll try to make sure I see those as much as possible. And if you have any questions, that I can answer after class, go ahead and set up a meeting by emailing me, and we'll set up a Zoom meeting, and we'll have an individual office hours. That seems to be the best way to do it. That way it's best associated where you get to ask the questions you need to ask. So go ahead and we'll do it that way until it becomes that too many people are doing that. And then we'll try to have a weekly scheduled one. But so if you need help, please communicate now. It's very important. We have a test coming up in a few weeks. So let's make sure we don't get behind on the game. All right, so we're still in chapter 3. We're supposed to finish up chapter 3 today, and we'll start chapter 4 on Tuesday of next week. So what we're going to do is we're going to muddle through the next few slides, and it's all about nomenclature. So we've talked about the nomenclature as a process, and we've gone through 6 of the rules of nomenclature already. Those 6 rules of nomenclature include finding the functional group, finding the parent chain, numbering correctly, looking at substituents, getting all these things down, looking at different alkenes and alkynes. So actually we haven't done alkenes and alkynes yet. But so the idea here is also go to Canvas. There is a nomenclature review page and functional groups that are on there that will take you all the way through all those steps in order. Now, you've been taking notes. To double check to make sure you have all of these rules in order, go to Canvas and download those rules of nomenclature. And that will tell you everything, even things we haven't studied yet, like stereochemistry are on there. So don't worry about that yet, but they should all be in that correct order. Okay, so moving on, looking at where we are in the system. Now we've added things to where we are having 2 or more substituents. And if they were the same, we could put them there. If they weren't, we had to put them in alphabetical order. And not only that, if they landed where we could number it, where 2 different substituents could be at the same lowest number, we identified the one that had the lowest alphabetical position as the one that should also have the lowest number. So that was rule number 6, okay? Now we're gonna add on to that rule number 6 with prefixes. Okay, the first thing we gotta do is that when we have 2 functional groups, we can say dimethyl, diethyl. However, those di, tri, and tetra are not included in alphabetization. It's only the substituent. So if you had 2 methyl groups and an ethyl group, the ethyl group would still come first because it's dimethyl, but you don't use the di, you have to use the M. Okay, so that's the key here when you were doing alphabetization, is it's for the substituent, not the number of substituents. Okay, so make sure that we have that there. Now, the iso in isopropyl is part of the word. So that's part of the name. And so that does count. However, numbers like di, tri, and tetra do not. Okay, so we've identified the longest chain, identified how to number it, trying to put the lowest number first. If we have alphabetization might play a role there. And now we have our di, tri, and tetra available to us as well. Okay, so now I want to stop a little bit about the naming things and talk about the classifications of types of carbons. This becomes important because it helps with certain names, like a primary alcohol means something and that. So I want to talk to you about classifications of carbons. So technically there is a classification of a carbon called methyl, which means there's only one carbon and it has no other carbons bonded to it. But every other compound has a designation of how many carbons are bonded to it. So if you have a carbon and it has only one other carbon bonded to it, like in an ethyl group, those are primary carbons, meaning they have one other carbon added to it. Okay. So if you have a carbon with 2 other carbons attached to it, we call that a secondary carbon. Okay. Now, a primary carbon will always have 3 hydrogens on it. So because we have to have a total of 4 bonds. A secondary carbon will have 2 hydrogens on it to make those 4 bonds. Now, moving again, adding 1 more carbon gives us our 3 carbons attached to a single carbon, which gives us our tertiary carbon. You could have up to 1 hydrogen attached to that to complete its 4 bonds. Now, move over 1 more time. So we have all 4 bonds possible bonding to carbons. We call that a quaternary carbon. Okay, so let's identify a few of these on this list here. And so I'm going to identify the primaries with the yellow here. And the primary is easy to recognize because it has the 3 hydrogens on it. So any carbon with 3 hydrogens on it is a primary carbon. Okay, so now if we move to the secondaries here, the secondaries you're going to want to see are, number 1, they have 2 carbons on it, and they typically have 2 hydrogens on them as well. So they're fairly easy to recognize. When we move on to tertiary, we're looking at 3 carbons bonded to it and a remaining hydrogen. And that takes us to our last happy folk here, our quaternary carbon. It's completely satisfied. It has 4 carbon bonds on it. It is done. Okay, so the primary, secondary, tertiary, and quaternary are how many carbons are bonded to that carbon. So notice that this is the quaternary carbon, but it has 3 primary carbons attached to it. Okay, so when we're talking about a specific carbon, we identify it as primary through quaternary. All right, so now that we have those divisions, those different classifications done, we can actually move on to taking a different approach on things. So instead of having these hydrocarbons be straight chains, what if they were in rings? That could be possible theoretically. So let's talk about cycloalkanes. So when you have a hydrocarbon that forms a ring, we call them cycloalkanes. alkanes or cyclohydrocarbons. Now, in the straight chain hydrocarbon, we have the general formula is CnH2n plus 2. Okay, and if we think about it, let's say we had 6 carbons. We're going to have a total of 6 carbons, and each of those has to have 2 hydrogens on it to give us 12 carbon hydrogens. And then we have the 2 hydrogens at the very ends that are the end cappers. We have to remove those 2 end cap hydrogens to create the new carbon-carbon bond to make the cycle. That's why our general formula is just the CnH2n. Okay, those last 2 hydrogens that were in the hydrocarbon are the ones we had to take off to make the ring. Okay, the most common of these are 5 and 6 membered rings, but they can be anywhere from 3 to 1,000,000 to make the ring. But the most thermodynamically favored are the 5 and 6 membered rings. So we're going to see those the most often. So how do we name these? Well, we have to name them by the number of carbons making the ring. So it's the number of carbons that make that ring. And then we call it cyclo. So if we have 5 carbons in a ring, we would call that cyclopentane. Okay. And then we would name the substituents off from there. If there is only one substituent, then we know where to start. We can start that substituent as 1, and it's always understood to be 1. Okay. If you have 2 substituents on there, like an ethyl and a methyl, you have to start with ethyl as the number 1 because it's the lowest alphabetical order, and then try to get the smallest number possible, just like our other rules on straight chain hydrocarbons. And if you have 3 or more, again, you want to get the lowest set of numbers possible, but when you write out the name, you're going to write them out alphabetically. So the lowest number of possible to assign the different substituents and then alphabetize them as we write the name. So let's do an example of that right here. So in this one right here, we have a total of 1, 2, 3, 4, 5 carbons in a ring. So that's telling us we have cyclopentane. Okay, but we have a substituent. And this substituent is attached here. So that makes this the parent chain and this the substituent. And this substituent has a common name. It's that one where we have the secondary carbon. We just learned about secondary carbons. The secondary carbon is the one bonding to the parent. And we call that the isopropyl group. So the name of this compound would be isopropyl cyclopentane. Again, the 1 is understood because we only have 1 substituent. Okay. However, if we have 2 substituents, we now have to make sure we identify them in their alphabetized order. Okay, so in this case here, we have a total of 1, 2, 3, 4, 5, 6 carbons in a ring. Okay, so 6 carbons in a ring makes it cyclohexane. So that's easy to know. But we have 2 substituents. We have a methyl substituent here, and we have a T-butyl substituent here. Okay. Remember, when alphabetizing, we don't use the hyphenated tert, sec, and we don't use di, tri, tetra. So that means the B is the one we're alphabetizing for. And since it's the lowest alphabetically, it becomes number 1. And so this is the 1 carbon, 2 carbon, 3 carbons, 4 carbons, which puts our methyl group on the 4th carbon. Okay, so this is great because now we know unambiguously exactly where that big T-butyl group is and exactly where that methyl group is, even though it's a ring and you could go around and around and around. We identify it specifically such that we know exactly where it is. So our final one is 1 tert-butyl dash 4 dash methyl. And if this weren't on another line, this wouldn't be a dash. They would roll together. The prefix and the parent run together without a break. All right, let's get a little more fancy here. This right here is the isobutyl group. And because isobutyl is the name of the group, it does count for alphabetization. Okay, so we have a ring here of 6 carbons. So we have cyclohexane. We have 2 groups on there, the isobutyl group and the methyl group, making this the 1 carbon and this the 2 carbon, because isobutyl is alphabetically lower than methyl. And then we can do that again with a little tiny ring right here. This little tiny ring is 3 is propane, so we call it cyclopropane. And notice that they're both on the same carbon here. So that means that must be the 1 carbon. We only have to identify 1. So we just have to do them in alphabetical order, and we get 1-ethyl, 1-methyl cyclopropane. Okay, so we see how this runs. Okay. Now, the only problem here is if you have a cyclohexane or a cyclic compound here, and we'll call this cyclobutane right here, and you have a longer straight chain, okay? The parent is always the longest continuous chain or the biggest ring. So if this chain has 6 carbons on it and this ring has 4 carbons on it, you actually name the cyclobutyl as a substituent on the parent because it has the greater number of carbons. Okay. Just a subtle rule, but don't worry, I probably won't need to use that anytime. Okay.
I have a quick question.
Yes.
Could you just repeat one more time when the putting things in alphabetical order is important versus when it's not a thing?
Well, there's 2 times. Okay, the first time you always put them in alphabetical order when you write out the name. Okay. Now, there's another rule that says to identify the number. Remember, we have to locate a number for each of them. On a chain where you have 2 substituents that are different. And if you go from one side, and let's say it's methyl and ethyl, and your methyl is on the lowest number, let's call it 3, or your ethyl is on the lowest number, also 3, you actually number from the lower alphabetical side. That is the preferred side. So in the case of you're numbering a long chain and your first substituent is either an E or an M, you number it from the side where the E is, the ethyl group first. Okay, so those are the 2 alphabetization rules related on how we number and how we name. Okay, with the subtle thing that di, tri, and tetra don't count, sec, tert don't count, but iso does. Okay, and those are all listed on that review on Canvas. Does that answer your question?
It does. I think I just need to practice it a little bit.
Yeah, it does take a little bit of practice, and if you practice using the sheet from Canvas, all of them are in order, and so you keep going down the list. And if you can answer, if you're only using the first 4 rules and you're done, you're done. You don't have to worry about anything. The only time you have to use the additional rules is when you have things that aren't obvious or things that aren't unambiguous. Then you have to continue on down the rules. Okay. So sometimes you can stop at rule 3. All right, so that's how we name our hydrocarbons, okay? And so these are all hydrocarbons with either a ring or a straight chain, but only having single carbon-carbon bonds, okay? So all of those are denoted having that system. Now, let's add a little level of complexity, but this system tells us a lot, okay? So we're going to talk about the prefix, infix, suffix system. Okay, so prefix is the beginning of the chemical name. In the beginning of the chemical name, we're going to have all the substituents listed and the number of carbons in the parent. So if our number, so if we only had 1, it'd be meth, and then for 10, it would be deca or dec. So it's that number of carbons is our prefix. Okay. The second thing we have are the letters AN, EN, or YN. AN, like in decane, says we only have single bonds. If we have even 1 double bond in that 10 carbon change, it becomes decene. So the EN signifies we have double bonds in that structure, at least 1. And if we had a triple bond in that structure, we have the YN. So it'd be an ine, decine. Okay, so, and then the suffix is the last part of the system, and it tells us what the functional group is. So this is a very important function here, is you have your substituents in the prefix and the number of carbons in your parent chain. The infix tells you the nature of the carbon-carbon bond. Single bond, double bond, or triple bond. If even one triple bond or double bond shows up, you have to indicate it with the ene or the ine system. And then the suffix is the last thing it tells us the class of our compound. For alkanes, it's the E at the end. Like in butane, the E at the end tells us we have a hydrocarbon. Okay, so we have the number of carbons. So that's easy to that's understandable. We now have the infix that says, okay, single bonds, ane, double bonds, ene, triple bonds, ine. But the last thing, the suffix, class of the compound. Okay, now we've been using this E in the end of them up to now, right here. And that's because we were talking about hydrocarbons. However, if we have some other functional group on this chain that changes the name of the compound, it changes the suffix. So for example, if we have an alcohol, which is a OH attached to the carbon anywhere on a hydrocarbon chain, we'll change the name from hydrocarbon to alcohol. And therefore we have to drop the E and add an OL. Each class of compound has a different suffix, so you can immediately tell which of the compounds are which. If we have another structure, this is called an aldehyde. This is where we have a structure where we have a carbon double bonded oxygen, and it's bound to at least one hydrogen. That's an aldehyde. The name of the end name changes. We drop the E and add AL. If we have two carbons bonded to a carbonyl, that's called a ketone. And so, like the name suggests, ketone, we drop the E and add the ON. So aldehyde has al, alcohol has OL, ketone has on, and carboxylic acid has ic acid in it. So we call it that, drop the E and add oic acid. Okay, so that's the suffix. That's why up to now we've only been using E because we've had hydrocarbons, but we need to drop that E whenever the functional group changes. Okay, so that's the value of understanding prefix, infix, and suffix. Okay, do we understand that now? All right, no complaint. Well, no auditory complaint. So let's look at how we can use the prefix, infix, suffix to name any chemical compound. Okay, so if we look at this compound right here, we have 3 carbons. So we know its prop is going to be our prefix. Okay, we have a double bond. So our infix has now changed to E, N, E. And we have no other functional groups, so we keep the E at the end. Our name is propene. Okay. Every letter has a function there. So there are no extraneous letters. Every letter serves a function. Okay. So let's go down and let's take 2 carbons, but put an OH on it, right? So 2 carbons is F, right? We have no double bonds, so we have to use the AN again. And we have the OH at the end of the thing, changing the name from a hydrocarbon to an alcohol, so we have OL at the end. Gives us ethanol. Okay, here we have 4 carbons and a ketone, but no double bonds other than the carbon-oxygen double bond. So we have bute for 4, ane for the single bonds, and on for the ketone, butanone. Okay, let's change that into an aldehyde by putting the carbonyl at the end and adding that, but we still have 4 carbons here. Butanal. And it's butanal, not the other way to pronounce it, by the way. Anyway, so if we change that simple 4 carbon chain into a carboxylic acid, we're going to end up with bute for 4, and for no double bonds, oic acid, butanoic acid. Okay, so that's the value of understanding prefix, infix, suffix. All right, and let's extend that up to cyclo compounds. We have an alcohol on a cyclohexane here, cyclohexane all, cyclohexanol. We have 2 carbons with a triple bond, eth, ine, it's still a hydrocarbon, E at the end, ethine. And let's take ethylene and change the functional group, turn it into amine, ethanamine, ethanamine. So everybody getting that? That's why we can just look at the chemical name and know its chemical class immediately by looking at those last letters. All right, so any other questions on this system here? Because once you play with it a little bit, it's going to make a lot of sense and you're going to be really happy that it's so systematic.
So why weren't the double bonds attached to the oxygen counted for things like butanone?
Okay, because it's a double bond between a carbon and an oxygen, that functional group is called the carbonyl. And the carbonyl actually is used in a bunch of different functional groups, so they all have different names. See, we actually have 3 of them right here. We have the carbonyl as a ketone, the carbonyl as an aldehyde, and the carbonyl as a carboxylic acid. So the carbonyl itself doesn't count as a functional group. It's how it's arranged otherwise. Okay?
I see. It's only meant for, you only use EN when it's carbon-carbon, that's right.
Correct. Carbon-carbon double bonds. Yeah, actually, that's a great distinction. Yeah. EN is for carbon-carbon double bonds and YN is for carbon-carbon triple bonds. We will see a carbon-nitrogen triple bond. That doesn't count. We'll see carbon-oxygen double bonds. That doesn't count. It's only a carbon-carbon bond. Thanks for the clarification. That was important. Okay, so we have different classes of compounds. We have different substituents. And we now can hook them into a bunch of different ways. So we have to talk about conformation. Conformation is the 3-dimensional arrangement of atoms in the molecule. And the interesting thing is single bonds can rotate, okay? There's nothing keeping them in a fixed space except for what the other atoms attached to it. If they get really big, they don't want to rotate. So what happens is sigma bonds can rotate. Okay, pi bonds don't. But sigma bonds, if you only have single bonds, that means every single bond in that molecule can rotate, leading to a bunch of different possible configurations. We usually draw them out straight, but they don't stay that way. Okay, so the first conformation we want to talk about is what we call the staggered conformation. And the staggered conformation is where all the groups attached to that sigma bond are spread out as far as possible from each other. Okay, so let's look at that. Okay, so if we did this ball and stick structure here, and we're just looking at one carbon next to the next carbon here, that carbon-carbon bond can rotate. Now, that doesn't mean this carbon-hydrogen bond doesn't rotate. It does. It's just it doesn't look any different when it does. So we're not really caring about that sigma bond to the hydrogen, but we do care about the sigma bond to the carbon because it can rotate. If it rotates, there's we can see that these hydrogens are going to be going around either clockwise or counterclockwise, and then these can also go there, which gives rise to different conformations. Okay. To make this a little more obvious, what I want to do is to, instead of looking at this double bond on end like this, we're going to rotate that 90 degrees. So we're looking down this carbon-carbon bond, and so we can see where the hydrogens show up. So as we slowly rotate that, we can see there's one carbon now in the back, and I'm going to change the color on these so that we can look at that. I'm going to put this, turn this into the blue carbon and turn this into the red carbon. And what we see is the red carbon's coming to the front. And if we rotated the full 90 degrees, we're going to end up with a red one in front of the blue one. So we barely see the blue one at all. But we do see the 3 hydrogens attached to it. So I'm going to start with these 3 hydrogens over here as blue hydrogens. And when we rotate them around, they are staying attached to that blue carbon and are these hydrogens. Let's do the same thing for the red hydrogens here. Okay, So this is a red hydrogen, a red hydrogen, a red hydrogen. So see how we've rotated it about 65 degrees, and now we're going to rotate it the rest of the way 90, such that these hydrogens are in front and these hydrogens are in back. Okay, so do we see how we're just looking at down that carbon-carbon bond? Now, when we do that, we can simplify that structure by drawing it, instead of the ball and stick, drawing it as what we call a Newman projection. Okay, so this Newman projection is exactly like the ball and stick, but it's easier to draw because the red one is the one in front, is the line, the three, like a propeller. Okay, the blue one is represented by the ring in the back, saying that there is something back there, and these are the hydrogens attached to it. Okay, so the way to remember that is the hydrogens are touching the ring, are bound to the carbon that's the ring, which is the one in the back. The hydrogens here in the front are actually meeting in the front, so they are on the front carbon. So now we can see that in this structure, as we turn it there, that the hydrogens are spread out as far as possible. Okay, they're equidistant from every other hydrogen nearby, and that is what we call our staggered conformation. So staggered conformation is when we draw our Newman projection and the hydrogens are as far apart as possible. Okay, so you can take any structure now, as long as you know where the hydrogens are, rotate it and draw a Newman projection. Now, we can do the same thing with things other than hydrogen too, and we will do that soon. Okay, so does everybody understand the concept of the staggered configuration? Okay, they're spread out as much, and you might have to practice a couple of times rotating that and making that Newman projection, but I'm going to do a few more, and so hopefully you'll get the hang of it. Okay, so doing that same thing, but instead of having that staggered configuration where they're spread out as far apart, what if we just changed it so we sat it down on like a table? So we had 4 hydrogens acting as legs, 2 hydrogens acting as a head and a tail, and we turned it into the Newman projection. So if these are all sitting on the table, that means they're all going to be lining up. So those are going to be, the ones sitting down here are going to be lined up with each other, and the ones on the top are also going to be lined up with each other. So that means the hydrogens are overlapping each other. Okay, 100% overlap like that is what we call eclipsed right here. So we go from staggered to eclipsed when the substituents line up with each other. Okay, why is this important? Well, it takes less energy to be in a staggered configuration than the eclipsed configuration. That's why our lowest energy conformation for anything is the idealized straight chain hydrocarbon, where they're all in that zigzag form. That fully zigzag form is the fully staggered conformation. Now, do they stay that way all the time? No. Any heat in a liquid, there's enough heat in the liquid to let those bonds rotate. And so some of the molecules will look like this, but then there's a lot of other conformations available to us for that. Okay, so we have eclipsed and we have staggered right now. We have another one, but it's only when we have substitutions. Okay, so let's talk about why it's less energy. Okay, so the concept of torsional strain is that when we have an angle between a total of 4 atoms, so we have an atom, and then, so we have a total of 4 atoms, and we look at it on the side here, the angle between them changes when they are staggered like this than when they're eclipsed. Okay, so if we look at the angles when they're staggered right here, they're far apart. Once they start to eclipse, the angle actually gets bigger because the eclipse is forced, because the 2 atoms that have electrons on them are starting to repulse each other, the angle gets bigger. And this is what we call torsional strain. It's straining the angle between those atoms. Okay, so it takes more energy to be in the eclipsed station than in the non-eclipsed station, because as we rotate, they start to spread out. And we've actually measured this to be about 3 kcals per mole. Okay, going from the staggered configuration to the eclipsed configuration. So that means that when available, it wants to stay in this lowest energy conformation. However, if you have at least 3 kcals per mole of heat laying around, it will allow it to do that rotation, and it'll make that staggered and the eclipsed conformations. Okay, does that make sense? That these hybridized, the sigma bonds can rotate, and that there would be a difference in energy where they're lined up and where they're not lined up. Okay. We're going to add on to that. Okay. So, okay. I have, so let's talk about when you don't have the freedom available to you when you have the straight chain hydrocarbon. So when you're straight chain, you can move around. There's really no barrier to it moving around and doing that. However, if you make a ring out of it so that it can't completely get out into that lowest energy conformation, we now have what we call an angle strain. So because we're forced to be at a certain angle that's less than or greater than our idealized 109.5 degrees for our tetrahedral structure, we end up getting strain from that too. So in the case of cyclopentane, if they were planar, it actually has an angle slightly lower than 109, letting somebody in the room here, and it's 108. And that's just enough to actually be able to measure it. You can measure that strain on there. And so what that means is that for smaller ones, it's even a higher strain, and maybe even some bigger ones, there are other strains. But this strain arises from the fact that it cannot either, it can't move around to optimize the value. It's fixed in that place in space. So the ring has that problem with it. Okay, so it's fixed there. It can't go fully, it can't go fully, in its ring state because it can't move very much. It stays in its fully eclipsed state if it's flat. Okay, so that means we have to add 3 kcals per mole for every eclipsed hydrogen in there, and that's what we call that strain, that ring strain. Well, there is an opportunity for it to actually, instead of being flat, if it pops one of those carbons up to give a staggered conformation, and then for it can actually release some energy and get into a different strain. And so what happens there is it goes from being a flat molecule to being what we call a puckered molecule. But notice that right here, instead of all of these being, in that eclipsed formation, we are able to get a staggered conformation for at least a couple of those atoms. The other ones are still eclipsed, but we can actually get one of them there. And so while this is a better thing for the eclipsed angle, the angle actually decreases, and it actually goes down to 105, making, even though there is less of the eclipsed conformation, the actual angle gets smaller, and therefore it's not the favored conformation. The favored conformation is the fully eclipsed one, because the combination between eclipsed and angles allows it to balance out those two competing energy wells, those two competing ways that are chewing up energy. Okay, so staggered is less energy than eclipsed, and rings, if they can't get to that 109.5 degrees, have strain associated with them. So 5 and lower, but 6 might be just right. Okay, so let's talk about cyclohexane. Why? So we've shown that 5 and lower will have ring strain because they'll have eclipsed. I'm sorry, they'll have eclipsed hydrogens around them. Cyclohexane is actually the first ring where we can get to what we can have all of them have a staggered conformation. Now, when we do this by the staggered conformation, it is not flat anymore. Okay, if it was flat, it would have all of the hydrogens be in a staggered, in an eclipsed form. However, there's enough flexibility in that six-membered ring to get to them all to be staggered. Now, when they're in their staggered form, I'm going to pull this up, we call this the chair conformation. And if you can think of it as, so imagine you have a chair looking like that. So this is what we call the chair conformation. Okay. And this is our lowest energy conformation for a cyclo compound, because all of the hydrogens now, if we did a Newman projection of this bond, just this bond right here, we would see that the hydrogens are all in their staggered conformations. Okay. And we can go down each and every one of those carbon-carbon bonds and we'll see the same thing. So by the time we get to six-membered rings, we can actually have a little bit of flexibility to make them be in an entirely staggered configuration. And that's why it forms that structure. It's no longer flat, it's in that chair conformation. Okay, but it doesn't have to stay in that chair conformation, okay? It can move back and forth, okay? So in cyclohexane, we actually end up having two different types of hydrogens here, okay? Because if we look at it, and we're looking at it on edge now, and this blue line is going right through the center of this compound, right through the center of the ring here. And we look at it from the side, we see that there are three hydrogens sticking up and are all kind of could form the legs of a stool. And there's three hydrogens down here that are all sticking up and all conform the legs of the stool. And notice their bonds are almost perfectly in line with this single axis going through the middle. Okay, so if they're in line with that axis, we call them axial hydrogens. Okay, so that means all three of these hydrogens on that side and all three of these on the bottom are all axial hydrogens. Okay, okay, so they're the kind of closest together. Now we have 1, 2, 3, 4. There's a hydrogen back here pointing down and a hydrogen back here pointing up. We have a total of 6 other hydrogens that aren't aligned with the axis. Okay, but if we think of that cyclohexane as a globe, they're around the equator. Okay, so that means we have 6 equatorial hydrogens as well. Okay, so what does that mean? It means the 6 equatorial hydrogens are equivalent and the 6 axial hydrogens are equivalent to each other. Okay, and this is in that chair conformation, that lowest energy conformation. All right, do we see how we have 2 different types of hydrogens, ones that align with that center of the ring and the ones that are sitting out from that ring. So we have 2 different types. Okay, so does it have to stay in that chair conformation? No. If you have enough energy, it can flip up one of the sides such that 2 of the carbons are facing up and 4 of the carbons are below it. Okay, we call this the boat configuration. Let me show you what it looks like. Okay, so the only thing we've done, we haven't broken any bonds. We're not going to break any bonds doing this in a conformation. We're just going to pull this bond up right here. And when we do that, we end up with that one puckered up. This one was already puckered up. So now we have 2 of these carbons up. Okay, but it is not as stable as the chair conformation. And the reason is that the hydrogens here, remember, they have an S cloud of electrons around them. And this has an S cloud of electrons around them. They start to butt up against each other. Okay. Now, because this configuration is called a boat configuration, the hydrogens that are butting up against each other are what we call flagpole hydrogens. So imagine flags at the front and the back of the boat. They are closer together than if we had flipped it back down to the chair conformation. Okay, so this gives rise to a couple things. One is that the boat conformation is less stable, okay? Meaning it takes more energy to hold it in that position. And it's because of the torsional strain by getting these eclipsed hydrogens at the bottom and these eclipsed hydrogen, these flagpole interactions at the top. That's a steric interaction. And the ones at the bottom are a torsional interaction. So we have torsion plus sterics giving us a higher energy. Okay, so that's why, again, the boat configuration here is the lower energy one. All of those hydrogens are staggered. None of them are impinging or butting up against anybody else. And that gives us a much less energy. So in this case here, yeah, 6 kcals per mole, higher energy than the chair conformation. Now, do they flip back and forth between those two? Yes, yes, they do. And depending on how much heat is in the system, they can flip back and forth very rapidly. However, because this is the lower energy side of it, more of the molecules are going to be in the lower energy configuration than in the higher energy configuration. Okay, so when we put multiple rings together, we'll see that the collection of those rings are going to start to form. It's flat, but it's not planar. And when we, for example, in this section here, this is an example of cholesterol. It's a steroid used in the body quite well. We're going to have 1, 2, 3 6-membered rings and a 5-membered ring all linked together. And what we see in that is that that's going to give these right here in this system. And all 3 of those rings, those 6-membered rings, are going to be in the chair configuration. And the last one here is going to be in that puckered configuration, trying to give it a slightly bigger. So we can look at that as saying, oh, because of where the molecules are attached and where these other things are added here, it's going to find its lowest energy conformation. And in its lowest energy conformation, all of those 6-membered rings are going to be in chair conformation. Okay, so let's talk about that chair conformation. Okay, so if you have a chair conformation, you have 3 axial hydrogens on the top, 3 axial hydrogens on the bottom, and the 6 equatorial hydrogens on the outside. Okay, but if you flip it to the other chair, the ones that were equatorial become axial, and the ones that were axial become equatorial. Let me show you that. Okay, so in our structure here, let's call the red hydrogens around the outside our equatorial hydrogens. And then let's just look at this hydrogen here. Okay. So in this configuration, this is one chair configuration. However, if we were to pull on this carbon and pull it up, pull on this carbon, pull it down, it would give kind of like the mirror image chair position of the cyclohexane. See if we pull this one down. Now, if we do this, that means this red hydrogen is going to be on the top as an axial, and this hydrogen is going to end up equatorial. Okay, so let's look at it over here. So all we've done is moved 1 carbon up, 1 carbon down, the 4 in the middle stay the same. So now that hydrogen that was yellow is now in an equatorial position, and the hydrogens that were equatorial are now axial. Okay. So are they different in energy? No, both of these are equal in energy until you change the size of the group attached to it. There's no energy difference between this chair conformation and this chair conformation until you put something on the ring that's bigger than a hydrogen or is different size than the other atoms attached to it. All right, so what happens? Okay, well, let's do something simple. Let's take a hydrogen out and put a methyl group on there. Okay, so we're going to do that same thing. We're going to start with one chair where we have the methyl group in the axial position here. And we're going to pull this carbon up and we're going to pull that carbon down to give us our other chair position. So our equatorial methyl group goes from being equatorial to being axial in the other configuration. Okay. So now we have a difference in energy. We have a difference in energy because the methyl group is bigger than a hydrogen. Over here, we only had 4 axial hydrogens. Those are the ones closest to each other. Over here, we have 2 axial hydrogens and a methyl group. The methyl group is 4 times larger than a hydrogen. So we start to see a problem. So let's use a space-filling model to figure out what that looks like. So in this right here, we have a space-filled model where all the outer spheres are those hydrogens. That's where the electron cloud of those hydrogens would be. Okay, and you can see that right here we have 1, 2, 3 hydrogens, all kind of facing up. Those are our axial hydrogens, and there's a little space between them, in between each of them right here. Now, if we do the same thing and we look at the hydrogen of the methyl groups, the hydrogens right here, and now this methyl group right here, boom, it's crowding out those other hydrogens. The carbon electrons and the electrons around those hydrogens are impinging on those other hydrogens. They are creating strain by having that interaction there. And that's what it would look like as a stick model here. So in the case of all hydrogens, both chair conformations are the same. However, once the size of the group changes, that is no longer true. The configuration where the largest group is in the equatorial position is always lower energy. Okay, so we always want to draw our lowest energy conformation is the one where our biggest group is in the equatorial or around the outside of the ring position. All right, questions on that? So hexane, cyclohexane is one of those cool things because it allows us to have almost all the same interactions we have in straight chain hydrocarbons, but it keeps it kind of localized in an area. We can flip back and forth just like other hydrocarbons, and we can have a higher or lower energy states. So now what can we do with that? Okay, we can use it as a model for other things, but now let's talk about a different kind of isomerism. In the system, we can have what we call Cis Trans Isomerization. Isomers are the same molecular formula, just connected differently, okay? So they're arranged in space differently, sorry. Same molecular formula, same connection atoms. We're not breaking any bonds, but we are arranging the atoms differently in space, and they cannot be interconverted by rotation around a sigma bond. So what's that tell us? Sigma bonds can rotate freely, pi bonds can't. Okay. Okay. So we have this kind of cis trans isomerization in rings as well because we've locked it in space. Okay. So just like in a double bond, where the cis thing is where the 2 substituents are on the same side and the trans is where they're on opposite side, we see that same isomerization in cyclohexane because it can't just freely open. Okay, so when we have 2 substituents on the same side of the ring, let's go to red, like these 2 methyl groups here, we call that the cis configuration of our cyclopentane. Okay, so in this configuration, it would be 2 methyl groups at the 1 and the 2 position. So it's cis 1,2-dimethyl cyclopentane. However, if they're on the other side of the ring from each other, one on top, one on bottom, that creates the trans configuration. So it's analogous to imagining that there is a double bond here. And why are we imagining that? Because the double bond also doesn't rotate, but because the ring's locked in place, it doesn't rotate. So we have that same isomerism of cis, both on the same side. And if our double bond was here, we would have trans on either side there. So that's what we call cis trans isomerization. in cyclohexane, cycloalkanes. Okay. So there's a couple different ways to draw it. Okay. So obviously we don't want to sit around and draw these space-filled models here. That's going to take way too much time. So what we're going to do is we could draw it this way here. This shows really well what it has. But we have another way of showing this in a simple diagram. Okay. So we draw the ring flat, just like we normally do. And then we use dashed lines right here, dashed wedges, to show something going down below the plane of the paper. So the ring here is in the plane of the paper, and the methyl groups are either above or below the ring of the paper. So imagine, like the same here, this is your plane of the paper here, and your hydrogens are, your methyl groups are below that plane. In this case here, if this was the plane of the paper, we would have one below and one above. So how do we note that on plain paper? Well, we put the ring in the plane of the paper, and then the wedge line says below the paper, and dark wedge says above the paper. So that's how we can differentiate them. So here we have both of these are below the plane of the paper, and therefore it gives us our cis configuration. We have one below and one above. They're on opposite sides. That's a trans configuration. Okay, so this is the easiest way to show three-dimensionality in these systems, is by using those wedges. Dashed wedges for below the plane of the paper and solid wedges above. Okay. So let's demonstrate some other cis trans isomerizations shown here. And we again can use those wedges to identify where they are. In the case here, we have one methyl group below, one methyl group below. So that means one of them has to have that dashed wedge, one of them will have the solid wedge. We have two methyl groups on cyclohexane, so we have trans 1,4-dimethyl cyclohexane. So how would we draw the cis one there? Well, in this case, they're both below the plane of there, so we're going to draw them both below with these dashed wedges, which gives us the cis configuration. They're both on the same side of the ring, making them cis. Notice they're two bonds apart, but they're still on that side of the ring, okay, which makes them cis on the system, and we draw it with our wedge, where, of course, the ring becomes the plane of the paper, and we have cis 1,2-dimethyl cyclohexane. Now, these look like identical compounds, except one has a methyl pointing up and the other ones are all down. They actually can be isolated and are separate chemical compounds. They are arranged differently in three-dimensional space, so we must clearly identify them as such. And we have with the cis and trans isomerization nomenclature. Okay, so can we represent that chair in the conformation with the cis and trans as well? Yes, we can, but we need to pay attention to where the biggest group is. And in this case, it's the methyl groups. So we might have a preference toward one chair conformation to the other. So let's look at the first one we have here. We have methyl group in the axial position and a methyl group in the axial position, because this is the trans dimethyl. So there's one up and one down, and we can get them both in that axial position. Okay. Now, as we found out before, just one methyl group in an axial position is not the most stable. So we want to flip it so that we have them in the equatorial positions. So just by flipping it, so that we have a hydrogen in the axial positions now, the methyl groups are in the equatorial positions, it's more stable. It's going to spend more of its time in this configuration. Okay, so that means in the trans dimethyl cyclohexane, there's a difference in energy between those two common chair positions. What about that cis one? Well, if we look at the cis one, they're both on the bottom side, so that when we have one conformation, we have methyl group down, and we have this hydrogen is equatorial and this hydrogen is axial. If we flip it, this hydrogen becomes equatorial, this hydrogen becomes axial. But notice that we still have one equatorial methyl group and one axial methyl group, okay? Meaning that flipping back and forth, there's no change in energy. So that in this particular case, the cis conformation has no difference in either of the chair conformations, but the trans did. Okay. Oh, all right. Questions on that? Okay. We're right at 12 here. Go ahead and take a break, stretch a little bit, take a drink of something caffeinated. Okay. Now we're going to hit our last stretch, our last 20 minutes here. We're going to finish out this chapter, and we're going to start with continuing on with the Cis Trans Isomerization. All right. So what we're going to do is we're going to draw an alternative chair conformation for this tri-substituted cyclohexane and state which conformation is going to be more stable. So from our previous arguments, we want to have all three methyl groups equatorial if possible. But if not possible, we need to try to make it so at least two of the methyl groups are equatorial if possible, or if not, one of them can be equatorial. So what we want to do is we want to redefine this and see if we can draw this such that we have at least two of these on the equatorial position. Let's see. Oh, no. There we go. All right. So the first thing we need to do is we need to find some space to draw. Okay. And let's look at that. So we're going to do more hybridization work here. No, I'm going to redraw that same structure here, and we're going to try to convert it into that cis trans isomerization. Okay. So we had cyclohexane, and with a methyl group up, CH3, CH3, CH3. Okay, and we're going to convert that into a chair conformation. And what I'm going to do is I'm going to make sure we keep track of those by putting just the hydrogens opposite these carbons here. Okay, so the first way I'm going to do that is I'm going to draw it first where I'm going to put this one up and this one down to try to get to our first chair conformation. So that's going to give us our chair conformation right here. And on this one, the methyl group was up, so it's going to be equatorial right here. On this one, the methyl group was up, so it's going to be equatorial here. And this hydrogen was down, so it's going to be axial. This hydrogen is down, so it's going to be, hold it. Oh, that I drew that wrong, sorry. That methyl group is going to stay on the top of the ring. So it's going to be drawn in red with the CH3 with the hydrogen being equatorial. And let's see where the last one ended up. The hydrogen is going to end up out here because it was on the bottom. And the methyl group is going to end up CH3. Okay, so we have two, just by doing that, we have two of the methyl groups in axial positions and only one in equatorial position. So let's flip it to the other isomer and see if we can't change it. So instead of going in that direction where we moved down and up, let's go ahead and instead flip this side up and this side down and redraw that. So we're going to start with that original drawing there and do that. So that's going to give us a chair conformation that looks something like that and that and that. Okay, and our methyl group is going to be up here. Our methyl group is CH3 and our hydrogen is going to be there. So let's see where our other methyl group ended up. So it was on the top, so it's going to be out here, CH3, and our hydrogen was on the bottom, so it's going to be down here as our axial. So this is our equatorial This is equatorial. Now let's see what we have in the last one. The last one here, we're going to have the methyl group end up equatorial and the hydrogen end up axial. Okay, so in this case here, by flipping it the opposite direction, we ended up with 2 of the methyl groups in equatorial positions and only 1 in an axial position. And that has to be our lowest energy conformation. Okay, and let's see, there. Wait. Oh, okay. Almost there, not quite there. All right, so there's another one here drawing these cyclohexanes, and you can go and do it by yourself. Try to see if you can get them to do in those different conformations available to you. And there are some answers to that in the book as well. But go ahead and try to practice that. If you have to build a model to do it, to flip it back and forth, do it, because you'll see that how you can get as many groups possible in that equatorial plane. It's going to be the most stable conformation. Okay, so let's talk about some physical properties of alkanes. Okay, alkanes are nonpolar compounds. Okay, carbon and hydrogen have approximately the same electronegativity, so it's a nonpolar bond, and therefore they don't have any strong forces between them. However, there is a very weak force that comes in between them, and what it's called an induced dipole. We call these dispersion forces or London forces. And what's happening is when this methane molecule, nonpolar molecule, comes close to this nonpolar molecule, it's going to say, well, you know, our electrons are trying to repulse each other. So temporarily, I'm going to move some of my electron density to the backside, making it slightly positive. And you can move some of your electron density to the same side, and they are loosely attracted by those partial opposite charges. Now, I said it's temporary because as soon as they move away from each other, they go back to being the way they were. So it's because they come in close proximity, you get this temporary induced dipole that allows them to be slightly attracted to each other. It's the weakest physical property force we have with our organic compounds. Okay, so what does this mean? Okay, because we only have weak forces with us, that means that the boiling point of our system is directly correlated to 2 things. One, the number of carbons. As you add carbons, the boiling points of these things go up. Every carbon you add, they go up. The other thing that does it is how straight they are. The straighter, the less branched they are, the more likely they are to have those induced dipole forces. So our low molecular weights from 1 to 4, so methane, ethane, propane, and butane, are all gases at room temperature. Okay. By the time we get to 5 to 17, these are liquids at room temperature, and anything higher than that is a waxy solid. Okay, or in the case of millions of units, which we'll talk about in chapter 16, polyethylene bags, which is a very strong polymer, is just millions of carbons in a chain. Okay. So that's how the molecular weight affects our physical properties. Well, we also have it, interestingly, is the carbon-hydrogen bond, because they're not really too well bonded together, that actually spreads them out a little bit, and they have a lower density than water. Okay, most hydrocarbons range around 0.7 grams per milliliter. Water is 1 gram per milliliter. That means most of these hydrocarbons will float on water. So I said there was 2 factors that bring us to our melting points and our boiling points. The first is number of carbons. The second one is how linear they were. And that all goes to that induced dipole effect. If you have 2 very long molecules that have the same molecular weight and they're coming together, you have a lot of different places where it can do that induced dipole force. However, if you have 2 molecules that are the exact same molecular weight, but they're more spherical or more branched, they have very few interfaces that they can make. The surface area is less, and therefore those van der Waals forces are not as strong, and therefore the boiling points are lower. So let's look at that in the table here. So our hexane, of course, is a nice straight chain hydrocarbon, 6 right here. And so that you can have another one come up next to it, and you have all the area in between here to have those van der Waals forces. Okay. So, and it has a boiling point of 69 degrees, low density and low melting point. Let's take an isomer of it and put a methyl group in the middle. Okay, that's this next one down here. When we do that, it makes it so that the only orientation that these can come together is with the methyl groups facing away from each other. And therefore we see a drop in boiling point because there's less interaction between the molecules. They can't link any way they want. So we actually lower the boiling point. And if we change it so it's not symmetrical now, so we have our methyl groups in a different location, that makes it even harder for them to link up together. And we see the boiling point drop again. Adding another methyl group to these, I'm sorry, not adding a methyl group, but moving the location of those methyl groups makes it harder to do that, and it drops. And by the time you get to the 2,2-dimethyl butane, where they're on the same thing, it's almost a sphere, and it drops again. So the two things that are changing this boiling point are the adding mass and that weak intermolecular force between the two things, the dispersion force. So as the available surface area goes down, the dispersion force goes down. Okay. So there aren't very many reactions we have with alkanes. In fact, the only thing we do with alkanes is we burn them because that's all they do. And so what we can do with that kind of study is we can actually compare the potential energy of all the different things by thinking about how much heat is released when we burn that substance. So we use this comparison of energy by calling it the heat of combustion. Things that contain more heat give off more heat. I'm sorry, things that contain more stored energy give off more heat when they're burned. So the great example is methane versus propane. So if you have natural gas only has a certain amount of energy in it. And when you burn that with oxygen to make CO2 and water, it releases about 886 kilojoules of mole. So that delta H means the change in enthalpy, which means it's giving off heat because it's negative. If you have propane, and it takes a little more oxygen to burn, it still makes CO2 and water. However, it gives off over almost 3 times the energy of the methane. Okay, so that means that methane has a lower heat of combustion than propane, which means methane has less stored energy. Okay, so we have a lot of hydrocarbons we use for storing energy, and they are a bunch of different sources. So natural gas is mostly methane and ethane. So if we think of natural gas that we come in our houses, it's mostly methane, a little bit of ethane, and an odorant to keep us from thinking. And that has a certain amount of energy. However, once we get up to things like propane and butane, they are actually more energy stored. And then we can use those as like propane cylinders and butane lighters. Okay. Now, the next thing up is what we call naphthas. Okay, naphthas also include that fraction of liquid that makes up gasoline. Gasoline has a lot of energy in it because it has all that carbon-carbon available to it, and it gives us that next thing. The next boiling section above that is what we call kerosenes. Kerosenes are also where we find diesel fuel. Diesel fuel and kerosene and air fuel are all in that kerosene level. A lot of capacity to convert energy there. Fuel oils are the kind of fuel oils used to heat houses on the East Coast. They're not very common around here, but then the last thing we have are the things that boil up to 350 degrees. These are things like the oil that you use to change in your car. Those are the next fraction up. And then everything else is what we call asphaltenes or asphalt. That's the black tarry stuff that you mix with rocks to make roads. Okay. So if you have these done, you can separate them out just by using their boiling points. Now, the other version of it is coal. Coal is a solidified version of carbon, hydrocarbons. It's usually a mixture with some other things in it, and it can be turned into these liquid materials, but it's not very easy. So how do we actually isolate those different fractions? If you've ever been to Houston and see the things with the flames coming off the top, that's what these are. These are fractional distillation systems. And the way that they work is you preheat the oil as it comes in right here. So you're warming the oil up such that it flows easily. And then you dump it into your distillation reactor. In your distillation reactor, everything that boils above 350 is going to be above this line. And everything that doesn't boil above 350 then drops down in the bottom and becomes the asphaltene residue. Okay, so things that boil between 250 and 350 stay in this blue zone right here. And then they get slowly fined off. Those that boil above that will go up to here. And if they boil between 175 and that 250, they're going to stay in this fraction and they're going to come out here. Now, for the next fraction, anything that boils in between these two sections is going to stay in that part of the column and is slowly going to drip out and be collected. Then our gasoline fraction's collected next. And then if it's not condensed anywhere in the system, what happens is it comes out the top. And it used to be that they would burn that off because it was hard to collect, but they've started to collect it now because it has a lot of energy associated with it. Those flares are burning all the time. So this is the major source of hydrocarbons we have available to us and how we can separate them all into our different classes of fuels that we use. Questions on that? And all right, so there is an opportunity to create combustible gases using coal, and we call this synth gas. And so what we've added to this the system is your coal is mostly carbon, and we can superheat it with water to create CO and hydrogen. Now, CO is called synth gas because we can use it to make a lot of other products. We can use it to make methanol, acetic acid, all these other things. So just the heating up of methane or coal to create that CO, carbon monoxide, and equivalents of hydrogen allows us a synthetic tool to, using a catalyst, we can create larger molecules or more useful things. Methane's a gas, it's hard to use. Methanol is a liquid, it's easy to transport. Methanol can be then converted into acetic acid, which can be used for other things. So we actually have a method for doing that, and it is by superheating these carbon-based compounds with either water or oxygen. Okay, I'm not going to talk about methane economy. And that is the end of chapter 3, which is where we hope to be at the end of today. I have 2 minutes left for questions if you want. Okay, I'm going to go ahead and stop recording and let you freely ask your questions without fear of being recorded.